Okay, guys, the rain has quieted down a little bit, so I'm going to continue on with these equilibrium problems. Here, just like the last video where I did an equilibrium problem at the very end, this one's the same thing. They want us to figure out what the reaction is, and then use the given Kc value and the ice table to figure out what are going to be the concentrations of the reactants and products at equilibrium. So we'll start with the reaction here. PCl5 decomposes to PCl3 plus chlorine gas. We'll set up the ice table. Concentrations initially 1 mole per liter for the reactant. We'll assume there's no product initially. The stoichiometry is pretty straightforward. We add those two lines together to get the equilibrium line. Then we can set up the Kc expression. Products over the reactants. Substitute in the equilibrium line. That's going to give us x squared over 1 minus x times x over 1 minus x. Unlike the last problem, which had a nice square in the numerator and the denominator, this problem doesn't have a square in the denominator, so we're going to be stuck solving the quadratic formula for this problem. So the first step is to rewrite this expression in terms of standard quadratic, form. So we'll multiply the denominator across. That's going to give us Kc minus Kc times x equals x squared. We'll put everything on the other side, so this will give us x squared plus kcx minus kc equals 0. So that's the standard quadratic form. It looks like, not squared, it looks like this: a times x squared plus b times x plus c equals 0. And then the quadratic formula, the roots are given by minus b plus or minus the square root of b squared minus 4ac. All of that divided by 2a. So that's the quadratic formula. In our problem here, a equals 1, b equals kc, and c equals minus kc. So we need to make these substitutions in here to get x. So we have minus kc plus or minus the square root of kc squared. And then we're going to have minus 4 times 1 times minus kc. So it's going to be kc squared plus 4kc. All of that divided by 2. So what I'll do is I'm going to go ahead and plug in the numbers just so you can see what they are. So the Kc value is 0.021. So this is the part that's very tedious. All of that divided by 2. Let's do it this way. So this I'm going to have a minus 0.011 plus or minus 0.0211. We'll square that, plus 4 times 0.0211. Take the square root, divide by 2, get 0.146. Now we've got two roots. One of them is going to be negative. Let's see, and that's not going to make any sense, right? It's not going to make any sense to have a negative value of x because that implies a negative concentration. So we don't want the negative value, we want the positive root. So we'll take the 0.146 and we'll subtract from that 0.011, and that leaves me with 0.135. That's moles per liter. Okay, so that is equal to the PCl3 and the Cl2 concentration. So we can say that PCl3, that equals the chlorine concentration at equilibrium. The PCl5 concentration, you take this expression here, it'll be 1 minus the 0.135, 0.865 moles per liter. Okay, so if I didn't make any errors, silly errors in my arithmetic, these should be the correct answers. It's very tedious to solve the quadratic equation. I usually don't put that on exam questions, but you will have to do this on the homework. Okay, so be prepared to practice doing the quadratic formulas for your homework evaluation. Let's see. All right. Well, the next couple of problems highlight some problems that we're going to be studying down the line. So what this problem is doing is it's a prelude to the acid-base chapter, which is the next chapter in the course. I'm going to go ahead and work this problem since it's an ice table and we can practice it. And I'll show you one of the tricks that we often get to use for acid-base ionization reactions. So here for this reaction, we've got hydrocyanic acid dissociating in water. This isn't my favorite way to express the acid dissociation. I would prefer to express it as a proton transfer reaction with water, like this. They're actually equivalent, but I prefer that form. Ice table. Our initial concentration of the hydrocyanic acid is 0.15 moles per liter. Pure liquid, we don't care about that. I should have put in the face. Pure liquid. It doesn't appear in the equilibrium constant expression, so we really don't need to consider it. Initially, we'll go over this later, but initially we'll take those to be 0. Usually I need to say that it's approximately 0. When we get to the acid-base chapter, you'll find out what I mean by that, because I'll do it again. Some of the acid is going to dissociate. That's going to give us some hydronium, and that's going to give us some cyanide. Add these two lines together. We get that. Then we take this equilibrium constant. They're calling it a Kc. Later on, we'll call it a Ka for acid. And then we substitute, we put in we set up the expression, and then we substitute in the equilibrium line. So that's going to give us x squared over 0.15 minus x. And it looks like we're going to have to do another quadratic equation. And you think, oh man, I really don't want to do that. And I'm right there with you. The good news is we don't actually need to in this problem. Okay? And the reason why is because Kc is so incredibly small. Okay? What does that mean to have a very small Kc? Well, a small value of Kc means that at equilibrium, you're going to have mostly reactants, hardly any products, really. Okay, so the smaller Kc is, the more reactants you have at equilibrium. Mathematically, what that means is that minus x is very small compared to 0.15. In fact, minus x is going to be an insignificant number compared to the 0.15. And so we can approximate this by neglecting the minus x and just saying that within sig figs, this 0.15 minus x is just going to wind up being 0.15. X is going to be smaller in magnitude than the precision of the 0.15. Okay? That allows us to make this approximation, which makes this a whole lot easier to solve. We don't have to do any quadratic equation. We just have to take a square root. So just to show you the numbers explicitly, plug in the value of Kc. And then we'll take the square root here. and you're going to get we'll just do 2 sig figs here, 8.6 times 10 to the minus 6, and that's going to be moles per liter. So that's going to be the concentration of the hydronium, that'll be the concentration of the cyanide, and the equilibrium concentration of the acid is just 0.15. Okay, so the reason we were allowed to make this approximation is because Kc is very small, which means that x is going to be very small. Indeed, 8.6 times 10 to the minus 6 is not significant compared to 0.15. So you can back substitute in and see, yes, our approximation is valid because x is too small. Now, occasionally, you'll have a medium, not a big number, but you'll have I don't know, something like 10 to the minus 4 for the equilibrium constant. Occasionally, you'll go at the end and you'll get x and you'll look and you'll see, no, x isn't small enough. It's significant compared to the number that's right here. So I need to go back and do the quadratic equation. Anyway, we will explore acid-base dissociation reactions in great detail later. Again, this is just a prelude, and it's another illustration of the ice table. Here's another one. This is a base dissociation reaction. It's very similar to the one that I've just done. You can get away with the approximation. This is small enough that it will work for you. And so why not go ahead and try to set it up for this dissociation reaction of ammonia. Let's see, this is a complex ion problem, and these are a real pain. These are some of the harder problems, harder equilibrium problems to deal with. I'm going to go ahead and do one of them for you. Let's do this one. So this is the type of reaction that you're looking at here. This is a complex ion formation reaction. So this guy right here, this copper ammonia species, is the complex ion. And you see that we have the bare copper ion over here, and we've got ammonia that attaches itself via coordinate covalent bonds to the copper ion. And then this thing is what we call the complex ion. Notice it has a very large equilibrium constant. Okay, so 5 times 10 to the 13. That implies that whenever you have any free copper around ammonia in aqueous solution, it is going to form this complex ion. In fact, most of the copper is going to be tied up in that complex ion. And in this problem, what we've got here is we've got some moles. So we've got 0.01 moles per liter of copper in the presence of a significantly high concentration of ammonia, and they want to know what are the concentrations of all of the species at equilibrium. Well, what you're going to find is that the free copper concentration is going to be very small. The ammonia concentration probably won't be affected that much, but it will change a little bit, and then almost all of this copper ion is going to be tied up in that complex ion. And so the way that I usually work these problems, for me, it makes most sense to work them in reverse. That is, instead of working them as a formation reaction, I'm going to work it as a dissociation reaction. So I'm going to take the reaction, I'm going to flip it around. I really only do this for the complex ion problems. And so you really need, if you want to follow my approach, you would recognize it as a complex ion, and then you'd say, okay, I'm going to turn the reaction around. So I'm going to write it like so. Basically, I'm making the assumption that all of the copper, I'm just going to put it all in I'm going to take all of the free copper and put it into the complex ion, and then I'm going to work it as a dissociation problem. And when you do that, you need to remember to take the reciprocal of the equilibrium constant. So the equilibrium constant for this reaction is going to be, I'm going to call this the Kd for the dissociation. It's going to be 1 over 5.0 times 10 to the plus 13. Right, we talked about this in one of the previous videos. When you turn a reaction around, you take the reciprocal of the equilibrium constant. So we'll set up the ice table now. Now, like I said, the assumption is all of the copper is tied up in the complex ion. So if we had 0.01 moles per liter copper 2+, and I put it all into the copper complex ion, that means that the concentration here is 0.01. No free copper, right? We chewed all of it up. However, the ammonia concentration is not going to be exactly 1. We need to take into account that some of the ammonia was used to form the complex ion. So what it's really going to be is 1 minus 4 times that number. And the reason for that 4 is because there are 4 ammonias tied up in the complex ion. Okay, so this will be the initial number for the ammonia. .96. Now, the change line. Okay, so now some of the complex ion is going to dissociate. That's going to give us a little tiny bit of free copper. And then that's going to produce, we're going to get back some of that ammonia. 0.01 minus x, 0.96 plus 4x. Okay. You would then take the KD value, set up the equilibrium constant expression, divide that by the complex ion concentration, and you take x, you would take then 0.96 plus 4x, then you'd have to take that to the 4th power, divide that by 0.01 minus x. So we're looking at a degree 5 polynomial here that you would need to solve to find x. The quadratic formula is bad enough. I couldn't imagine having to do a degree 5 polynomial. Actually, you can't. You'd use a computer and it'd actually be pretty fast. But in any case, we don't have to deal with this degree 5 polynomial. We can take advantage of the fact that KD, I'm going to calculate the numerical value right now, 1 divided by 5 times 10 to the 13, 2 times 10 to the minus 14, is incredibly small. Okay? As a consequence of that, we know that most of the copper is going to be in the complex ion. So we're anticipating x to be extremely small. It's going to be much less significant than 0.01. And so we can approximate that as 0.01. We can approximate this as 0.96, right? Plus 4x is going to be insignificant compared to 0.96. So that allows us to simplify our expression here. Don't forget about the power of 4, though. Okay, it's much easier to find x now. X will be KD times 0.01 divided by 0.96 to the 4th. Yeah. So we'll take the 2 times 10 to the minus 14. That's the KD value times 0.01. And we'll divide it by 0.96 divided by 0.96 again. And I'm getting, I did do it to the 4th power. 2.4 times 10 to the minus 16 moles per liter. Okay, so that is the concentration of the free copper at equilibrium. And as promised, it's totally insignificant. Okay, so 10 to the minus 16 is completely insignificant compared to 0.01. It's completely insignificant compared to 0.96. So our approximation was justified. So the equilibrium concentration of the complex ion is just 0.01. There's hardly any free copper, if any. And then the concentration of the ammonia is just 0.96 at equilibrium. Okay, and so that's how you do these complex ion problems. I like to work them backwards. Here's another one for you to practice if you wish. I would solve it in exactly the same way, in the sense that I'd turn the reaction around, I'd calculate the reciprocal of the equilibrium constant. Yeah. Well, I'm going to go ahead and stop this video right here.